One way between subjects ANOVA in SPSS. So here I have an example data set. This comes from Professor Andy Field. So he wrote a fantastic statistics textbook. Anyway, we've looked at a couple of his examples. I think they're really great. So here we have two variables. So in this data set, he's looking at the Halloween costumes that children wore. So that is our first variable, hero. We have 4 different kinds of superheroes that these kids dressed up as. So we have one group dressed up as Spider-Man, another as Superman, 3 as the Incredible Hulk, and then group 4 they dressed up as someone from the Ninja Turtles. So we have 4 different groups here, and we want to know, based on how they dressed for Halloween, did the number of injuries or the severity of injuries that they incurred that evening while trick-or-treating, did that change? So here we have the severity of an injury rated from 0 to 100, with 100 being, is a more serious injury. 0 would be, of course, they didn't get injured at all. We're going to look at this by 4 categories: Spider-Man, Superman, Hulk, Ninja Turtle. Because we're interested in all 4 of these groups, we need to do an ANOVA. We could do a t-test of Spider-Man versus Superman, for example. We could do a t-test of Spider-Man versus the Hulk. But when we start to look at multiple comparisons like that, it inflates our family-wise error. So remember our discussion of error and how that's a bad thing and we want to minimize it. So that's why we're moving from t-tests into ANOVA. We can look at all of this stuff in one fell swoop and decrease our chances of error. So how do I do this in SPSS? We have our data view, so we can see our heroes, 1, 2, 3, 4, the injuries, we've got a 51, 31, so on and so forth. So that's the severity of injury by the type of hero. Now if I want to look at an ANOVA, of course, first we want to check some of our assumptions, right? So you would go to Analyze, Descriptives, you could get your skew, your kurtosis, you could look to see if you have any outliers. Excuse me, we're going to skip that. I'm going to tell you right now, this data is fine. I use it every year. It's just a silly little data set. But if you are doing these kinds of things on your own with your own data, please do take the extra time to check those assumptions. They are very important. Now, since I've told you there are no violations in our assumptions here, we can jump straight to our analysis of variance. Go to Analyze, Compare Means, one-way ANOVA. Next week we'll be looking at a more complicated ANOVA. We'll have to run this a little bit differently. So I'll show you the second way to do this next week, but for now let's do it this simple way. Analyze, Compare Means, one-way ANOVA. Now you get this box that pops up. You have your dependent list, you have your factor. It looks very similar to the t-test. So of course our dependent variable is the injury severity. So we're saying depending on the hero, you'll have different levels of severity. Of course our factor, our independent variable here, is the type of superhero costume chosen. We have some options that we should check. So remember, an ANOVA is only going to tell us overall if there is a difference. If we want to get down and know which groups are different from which other groups, we need post hoc tests. So you check that, and you have all of these options, so many options. So we have equality of variance is assumed, or equality of variance is not assumed. So remember, from a t-test, we want the variances of our groups to be approximately equal. So if that is the case, we can run LSD, we can run Tukey. If it is not, typically Dunnett's T3 or Games Howell. So we'll check all of those, go ahead and run them just in case. Hit continue. Under options, remember we have some assumptions. We need to check homogeneity of variance. We do want those results. You can get descriptive statistics, so you can get mean, injury, severity by hero. Those kinds of things are sometimes important to look at. So I'm going to check descriptives and homogeneity of variance test. hit continue. The only other thing here is contrasts. We're going to ignore that. I don't think I've ever used that analyzing data, so I don't think there's any need to go through that right now in our intro course. After that, we hit OK to run it. Of course, if you hit paste, you can get your syntax so that you can come back to this later. Now we get a lot of stuff here. Starting off at the top, we get our descriptives. So we can see right off the top there were 8 people that dressed as Spider-Man, 6 Superman, 8 Hulk, 8 Ninja Turtles. We can see the means across these different groups. Ninja Turtles only had a mean severity injury rating of 26. On the other hand, Superman was up at 60. Then we can get our standard deviation information, minimum, maximum, all of that descriptive info that we've been talking about. Here's our test of homogeneity of variances. Remember, this is our Levene's test. We do not want this to be statistically significant. So our test of homogeneity of variances, we want it to be above 0.05. It is, so we can assume equality of variances. Remember when I was talking about the post hoc tests? If this number was less than 0.05, it would change which post hoc tests we could use. It is not. It is not statistically significant, so we can use LSD, we can use Tukey, we can use anything from that top box that we saw earlier. Now this ANOVA table should look very familiar with you if you've been working on your homework so far, or if you watched the other lecture. This is our summary table. We have our sum of squares between groups, within groups, total, our degrees of freedom, of course, k minus 1, our total n minus k. We can divide those out to get our mean square. Sum of squares between over degrees of freedom between will give us our mean square between. Sum of squares within groups over degrees of freedom within groups gives us our mean square within groups, right? And then if we want to calculate our F statistic, we take mean square between groups over mean square within groups, and that gives us our F statistic of 8.317. Here, SPSS is great because it calculates our exact p-value, but remember, when it says 0.000, it is rounding. So if you are asked to write this up, you would report it as p is less than 0.001. Now you have to ask yourself, is this statistically significant? Is there a difference in groups? Does the excuse me, does the outfit, does the costume that these kids chose, did that cause them to have different severity of injuries here? With a p less than 0.001, the answer is yes, this is statistically significantly different. These groups are different. Now, how do we know which groups are different? That's our post hoc test. So if we scroll down here, I checked a bunch of different options. We know that we didn't have any violations. We can ignore this bottom Games Howell. We can ignore Done It T3. So then we have LSD, and we also have Tukey's HSD. So we're just going to look here. We have some comparisons. Spider-Man versus Superman. We'll look at the p-value 0.058. Spider-Man versus Hulk 0.7, Spider-Man versus Ninja Turtle 0.107. Let's see. Superman versus Hulk is 0.007, so Spider-Man versus Hulk, there is a difference there. If we scroll up, Spider-Man 41.63 was their severity rating. Hulk was 35.38. So children that dressed up as Spider-Man had more severe injuries than children that dressed up as the Incredible Hulk. There's our result for that pairwise comparison. Now, if we keep going down here, Superman versus Ninja Turtles, our significance is less than 0.001. There is a difference here as well. Superman versus the Ninja Turtles, so Superman 60.33, Ninja Turtles 26.25. Children that dressed up as Superman had much higher injury severity ratings at a 60.33 than children that dressed up as Ninja Turtles. Their severity was 26.25. So it's kind of hard to read. I encourage you to run this, pull it up, take a look, and I usually print these out so that I can kind of highlight across, but it's going to give you one of your categories from your independent variable, another one, and then it will give you your significance. One of your categories versus the second versus the third. So you have every single pairwise comparison with an associated p-value. Same interpretation rules apply. If that p-value is less than 0.05, that pairwise comparison is statistically significant, and you can say those two groups are different. If that p-value is above 0.05, you have to retain the null, say that there is no difference between that pair, and you move on and look for your next comparison. Now, that is this table down here. You can just ignore. We don't really need that right now. But this is an ANOVA in SPSS. You'll notice that it did not give us our effect size again. So when you run ANOVA this way, you do not get your effect size. But remember, your effect size, eta squared, so remember that weird symbol, is your between group sum of squares over your total group sum of squares. So you can pull out a calculator real quick, take 4180 over 8537, and you can see what kind of effect size that is. So we can go ahead and do that real quick. 4180, 617 over 8537,200. Our eta squared is 60.68%. So that's a pretty large effect size there. So there is a difference here. It is a fairly large difference, and we can see Superman is getting higher injury ratings than Spider-Man and than the Ninja Turtle there, I think. No, sorry, I misspoke. Superman versus Hulk and Ninja Turtle. So Superman was higher in severity ratings than Hulk and Ninja Turtle, and of course we got that information down here looking at Superman versus Hulk was 0.007 p-value, Ninja Turtle less than 0.001. That's ANOVA in SPSS. We'll do more of this in your homework and then even more next week, so that gives you something to look forward to.